Yep. Yeah, so in those cases, from what I understand, it's it has kind of a regular kind of geometry. So I was like, most people, when you try to move your finger back, there's literally like a bone contact. That's and other people could do like weird stuff. Yeah. So it's usually like they have kind of a weird because there's variations in the bone geometry. And so for some people, they have a regular geometry that's stuff.
So it's just like a flexibility, or it's just
it's the bones of the joint, and so they have kind of a geometry that kind of lets them do more movement than typical. And so usually, and I think for most people they have usually it's because they have two stable
and they less prone to like injury because of that.
They're more flexibility you have, the more prone to injury. Exactly. So anytime when you have force like the more stability you have, the more flexibility you have, the more likely it is to.
Were you in the back of your home?
I did homework and just twice. I did. I don't want to deal with traffic. I live by the beach. Traffic up here after 3 or 4. It's very random. So I'm just like, you know what? I'll just come here early, do some homework, and then relax a little bit. I hear it too.
Yeah. I was like, is that me?
Sure it's fun. I'm not sure it's fun.
Yeah, I thought it was too, but I'm like, wait, I'm the only one here. Oops, that's not what I wanted.
Don't worry, you're not going crazy.
Oh, I'm going crazy, but usually it usually doesn't show up this early.
I have like no joint movement in my right foot. I have to do a very heavy surgery to get my foot straightened out. So I have no flexibility.
Oh, I see.
But I was listening to the joint thing.
That's okay. You're much less likely to get injured, so that's a good thing.
I have titanium rod too, so if
my gosh,
break a leg, then it won't be as harsh.
Dang! Wow.
Let me see if I can find that in Facebook. I posted on Facebook. Like extra. There's a lot of device on the right foot. It's because we would also rotate my leg, so and the foot didn't correct itself either, so we have to also do that.
I see.
Depends on traffic. Sometimes I get there, like they live in a very far place too, so like it takes me yeah, that sounds about right. I'm like 2 just like 10 minutes away. But yeah, SP. I've tried sir. That's not right. Sunday, Saturday. I'll take on this person. Saturday.
Oh yeah, those two computer guys were in here trying to fix one of the computers too. So
Okay.
they're probably doing something.
Oh, okay. That makes sense. 'Cause I don't think there's not a classroom here. Right? I'm guessing that's
Yes,
the server.
tech IT guys.
Okay.
Hi, hungry on Charles. Yep, that jokes. Oh, I say that all the time. Yep, this is it. Let me see. Is it possible I can show the photo? Am I right for X-ray on Zoom? Or
Just
recording?
just show me.
It's recording. I just realized. What it looks like.
Oh my
Right
gosh.
foot.
Wow.
Yep.
That's crazy.
And that's I still have that still. So
Wow.
it can't quite point
I see.
correctly. So
Well, marvel of modern technology that we
And
can
then-
do those things, but
and this was and here's my Elizabeth.
oh my gosh.
That's why I had to wear it for 2 years.
Oh, I see. Wow. That's crazy.
And he has to cut it in half so the rotation can work.
Oh my gosh.
So
Yeah. Marvels of modern medicine.
yeah.
That's cool though. It's a cool story you can tell people.
Oh, I tell them that all the time. I have the scars. I don't get rid of them. So I know there's some product you can just mostly get rid of, but I don't care. It also just showed proof that I had surgery too.
Yes. There you go.
Are we doing workbench today?
Yes, we are. So today is an Ansys case, so we're gonna be working in Workbench.
Shut off the lights in the hallway.
Just now because they're trying to conserve power.
And power.
Yeah. So it'll go back to normal.
Hopefully.
Yeah, we'll see.
It's weird. It's only this building they're doing it for business. They don't do it at all. They're just
They
like
got the money.
Yeah. Never mind.
the business.
I was telling I mean, you were here in last class. Like when I went back up to my office on Tuesday, it was freezing up there. Like the AC was on full blast. It's because the dean's up here. The dean makes all the money for us. Make sure she's comfortable.
The business, it's on high.
But in a huge lab like this with a ton of people and a ton of computers, we can't afford. We can't. We got to save power. You guys just gotta roast. That's how it is.
It's a woodbench, not something.
All right, it's 5:30, so let's go and get started. All right, good evening, everyone. We are on Ansys Activity 2, so it's an exciting day. So how's everyone doing today? Good, good. All right. Okay, I get a much better response when we have Ansys days. I think people are more excited for these. Okay, so the plan for today, this is the only thing we're going to work on today is just doing Ansys Activity 2. Okay. It's going to have a little bit of a different workflow, but it's still going to build off a lot of the concepts that we went over on the first activity. And so a lot of the things we did in the first activity, like I'm, kind of in that activity, I kind of held your hand a lot with the meshing and the boundary conditions. I'm not going to do a lot of that this time. I'm going to show you just general tips, but a lot of today is actually just going to be working on your own. So, I'm going to give you some of the new knowledge today, like how to import a part, how to change material properties. We'll go over that together. But a lot of the rest of the activity, is going to be you working on your own. Okay. All right. And so one thing I want to say is that I've been looking into the version mismatch issue. And so, for those who aren't caught up, the version of Ansys that we have here in the lab is 2021. But if you downloaded the Ansys on your own computer at home, that's 2022. And so what people are finding that it's you can't really load projects that you started here in the lab and brought home. Or it's more like you can't do vice versa. So you can't start one at home and bring it here because the versions are mismatched. And so I looked into it a bit. I don't have a solution, unfortunately, because the people I've talked to said that for the student version, the one which you download at home, they really only support the latest version of that. And that's mostly just because they want to kind of focus their support on just that one version. They don't want to keep supporting previous ones. And so actually, if you try to use the student version from 2021, you're actually not able to because all those licenses have expired. And so I think probably what's the better solution then is for me to talk to IT here and to try to get 2022 Ansys on these computers so that we can start using that instead of 2021. So I'm going to look into that. Hopefully we'll get that sorted out by the next activity. But just for this one, just keep in mind that, stuff, if you're working on the lab computers here, it's going to be difficult for you to move it back onto your home computer there. And so what I'm hoping today is that, I give you guys enough time to work on it where you can get a good chunk of the work done here and get your screenshots and everything you need for the report. Then when you go home, you kind of only just work on just other stuff that you need to, okay? And so I'm gonna try to make it so that we break it off at a good point where you don't have to kind of continue where you left off here. You just work on new stuff at home, okay? All right, so that's kind of where that's at right now. And so, I know I said I'd have a solution by today, but it was kind of a bigger issue than I thought. And so, I'll keep working on it, and then by next time, we'll have a better solution. Okay. All right. And so, any questions on anything? Okay. All right. So here is the activity for today. And so the subject of our analysis is going to be a bike crank. And so, if you're not familiar with this, the bike crank is the part which kind of connects to the bike and then connects to the pedal. And so it's kind of the mechanism that you kind of push down on, and it causes the bike wheels to rotate. Okay. And so kind of the setting, which is, not important, but I think it's always nice to have flavor text. And so kind of the flavor of this activity is that you're working for a bike manufacturer, and you're proposing this design here for a bike crank, and you're curious to know if it's going to break under some typical loading that it might see during operation. Okay, and so I'm going to give you the CAD model for this bike crank. It's not something we're going to make ourselves. We're going to load it in Ansys. You're going to apply boundary conditions, and we're going to see if it's going to break or not. Okay. And so I guess I should have said this, before we began, but if you haven't started up Ansys Workbench, now is a good time to do it, because Ansys Workbench does take a bit of time to start up. So I'll give everyone a second to load that up. Okay. And then while you guys are loading that up, I'm going to talk about some of the new knowledge that we're going to go over this week relative to the first activity. Okay. And so from the first activity, we went over what I consider to be kind of the essentials of Ansys. And so we made our geometry, we meshed the geometry, we applied boundary conditions, and we looked at the results. Okay, so those are kind of the essential steps for any Ansys simulation. You're going to do all of those steps. Okay, so today we're going to build on that a little bit. And so, instead of making our own geometry, we're going to be loading up a CAD file. Okay, so I posted a CAD file on Canvas for you to download. And then we're going to do some extra things like changing the material properties. We're going to be suppressing parts. And we're going to do a little bit more with the meshing that we didn't do on the first time. Okay. Okay. And so first thing you guys are going to need to do is you're going to need to download the CAD file. Okay. And so if you go to our course website, so let me click on student view. Okay. I don't know who they are. And so if you click on the Ansys activity 2 here, right, you'll see that there are 2 files for you to download. And so the file that we're going to need for the activity today is crank_assembly.x_t. Okay, so this is a parasolid file which we're going to import into Ansys. Okay? And so the other CAD file here is going to be used for an activity at the end of this one. And so what I'm hoping for is we'll finish everything with this CAD file, and then the only thing you're going to have to do at home is going to be work on this one right here. Okay. Okay. And so does everyone have Workbench started up on their computers? Okay. Okay, so let's go ahead and begin. And so first thing we're going to do is we're going to click and drag static structural over to the work area. Okay. All right. And so that's the first thing. And so we're making a static structural kind of analysis type here, which we're going to be working on. Okay. All right. And so if you recall from last time, we made our geometry from scratch. And so what we did was we basically opened up the CAD program within Ansys and drew our geometry. Today, we're going to be skipping all of that. And so, I provided the CAD file for you. And so let's go over how you import a CAD file into your project. Okay. And so what you're going to want to do is you're going to right click on geometry. You're going to highlight over import geometry. Okay. And then what you're going to do is you're going to click on browse. Okay. Okay. And so after you click browse, this kind of Windows Explorer thing will show up. And so you're going to navigate to the parts of your computer where you downloaded that crank assembly x_t file. Okay. And so it's going to show up, if you're on the lab computers here, it's going to show up as a SolidWorks file, but don't worry about it. You can actually load that within Ansys. Okay. So go ahead and you can either double click it or you can click open. Okay. And you should see the process is fairly quick. And so right after you click load, you'll see that there's, if it loaded properly, you should see there's a green check mark, you know, next to geometry with it. Okay.
With other modeling software.
So it has to be specific file format. And so for SolidWorks, I think the default file format for SolidWorks is an SLD PRT, something like that. And so that won't work in Ansys. And so you're going to need to export it as a certain file format. And so this is X_T, which is called Parasolid. And so that one works really well. The other types of files that work well are like a step file, STP or STEP. I'd say those are probably the most reliable. And so those you can export from SolidWorks pretty easily in those kinds, and you can then import them from Ansys. Yeah. All right. So was everyone able to upload their or import their geometry? Okay. Okay. And so, all right. And so before we jump into Ansys Mechanical, let's go ahead and add material properties. Okay. And so I think we started this last time, although we didn't need to. And so today we're actually going to do it for real. So we're actually going to make a new material property. Okay. And so what you're going to want to do is you're going to want to go to engineering data here. And then you want to double click it. And so when you double click engineering data, it's going to bring up this new window here. Okay. Okay. All right. And so what we want to do is we want to go to this part right here. Okay. And so if you look at the kind of the tagline here, it says click here to add a new material. Right, because if you read the project specs, you know, the material that our bike crank is made out of is aluminum 6061 T6, okay, which we don't have right now. And so the only material that we have right now is structural steel, and so we're going to need to add aluminum here. Okay, and so when you click on this window to add a new material, you can give it a name. So I'm going to call it aluminum 6061 T6. You don't have to name it that, but you know, I think it's helpful to name the material after what it actually is. Okay. Okay. And so after you hit enter, you'll see that it creates a new kind of material entry here called aluminum 6061 T6. Okay. But we're not done yet, because if you look here, you can see that there's kind of a blue question mark here next to that aluminum 6061. That means that we have to do something here before Ansys recognizes this as a real material. Okay. And what's missing from this is the actual material properties. And so all we've done is just give it a name. And so we need to assign things like the Young's modulus and the Poisson's ratio. Okay. Okay, so let's go here. And so we're going to assume that this aluminum 6061 is a linear elastic material. And so we're going to click on this plus arrow next to linear elastic. And then what we want here is isotropic elasticity. Okay. And so aluminum is just like most metals, and so it's an isotropic material. And so what that means is that it has equal strengths in all directions. Okay, so go ahead and double click on isotropic elasticity. Okay, and then after you double click that, and you go down to this bottom area right here. Okay, what you'll see is that you're going to be able to click on this plus arrow and expand this, and it's asking you for two things. And so it's asking you for the Young's modulus, and it's asking you for the Poisson's ratio. Okay. Okay, so let's assign the Young's modulus first. And so if you go back to the project specs and you look on the front page, okay, you'll see that the Young's modulus for our material is 1 × 10⁷ psi, and our Poisson's ratio is 0.33. Okay. So let's go ahead and assign these material properties to our material here. Okay. And so for the Young's modulus, you have to be really careful here, because I know some people ran into this issue last week. You want to make sure that you're using the right units for the Young's modulus. Okay, and so for this case, you know, the Young's modulus is given to us in PSI, and so you want to click on that drop-down menu and make sure that you've selected PSI from this menu. Okay. Okay, and so making sure that this is PSI right here, let's go ahead and assign the Young's modulus as 1E7. Right, and so that assigns our Young's modulus as 1 × 10⁷ psi. Okay, and our Poisson's ratio is going to be, make sure I have numlock on, 0.33. Okay, and so the Poisson's ratio doesn't have any units, and so that's all we need to assign for that. Okay. All right, any questions on this? Everyone is able to assign the material properties? Okay. All right, and so whenever you need to, load in a new material, which is very common in Ansys, most of the time you're not going to be running a simulation on structural steel. And so you're going to need to go through this process to add the material, okay? And so at the very least for a structural simulation, you need to add the Young's modulus of the material and the Poisson's ratio. But of course, if you have a more complex material that requires, more parameters, you can load that as well. But at the very least, you should include these two material properties. Okay, and so now that we've assigned aluminum 6061, we can go ahead and close this. Okay, so you can go ahead and close this tab for engineering data. Okay. And so the next thing we're going to do is we're actually going to open mechanical. So go ahead and double click on model. And that's going to open up Ansys Mechanical. Right, so mine opens up pretty quickly because I was testing it out earlier, but yours might take a couple seconds. Okay, so just give it a second. And if you have that weird kind of Ansys thing show up, it's like an ad. And remember, you can just click on geometry right here to kind of close that window down. Okay. All right. And so everyone was able to load up mechanical. Everyone's here. Okay. Okay. So let's go ahead and let's work on this a little bit. Okay. And so if you'll notice from this geometry here, it's actually an assembly. And so it's not just one single part. We have these three parts here. Okay. And so if you expand the geometry window, so you click on the plus window next to geometry, you can click on the different parts to highlight, what they are. Okay. And so you can see here that we have three parts. And so we have the pedal, which is this rod right here. We have the bike crank, which is this part right here. And then mysterious part number 9, which is that one right there, which is kind of a fitting that mates the pedal and the bike crank. Okay. And so you can definitely run the simulation with all three parts. But for assemblies, there's actually a bit more to it. And so assemblies is actually the subject of activity 3. And so for this activity, we're just going to focus on one part. And so we want to kind of get rid of these two parts right here, the part 9 and the pedal, because they're not going to be important for this analysis, right? And so when you have parts of an assembly that you don't want to make part of your analysis, what you need to do is you need to suppress them. And so by suppressing the geometry, you kind of effectively get rid of it. And to suppress the geometry, it's very simple. And so you just have to right click on the geometric part that you want to suppress, and then go down to suppress body right here. Okay. Don't click on hide. And so hide is not going to get rid of it. Hide just kind of removes its visibility. But when you hide a part, it's still actually part of your geometry. So what you actually want to do is suppress it. Okay. And so go ahead and right click on pedal and suppress the body. And then right click on assembly, part 9, assemb2, whatever, and then suppress that as well. And so at the end, you should just be left with just the bike crank. Okay. Okay. Right, so everyone was able to suppress those two parts. Everyone's good. Okay. All right, and so the last new thing that we're going to do, before I kind of let you guys go, is to actually assign the material property here. Okay, and so even though in Workbench, we created this new material called aluminum, we haven't actually assigned it to any of the parts. Okay, and so if you click on the bike crank part in the geometry, and then you go to the lower left-hand side of the screen, you'll see that there is a data section here for material assignment. Okay, and so this is where you can actually assign different materials to your part. Okay, and so right now this crank is actually made of structural steel because we haven't changed that material yet. And so to actually change that, you need to go ahead and click on it, click on the plus arrow, and then you're going to click on the aluminum material property that we just created. Okay. So let's go ahead and click on that. Right. Let me leave that up just in case. Okay. Right. And so after clicking on that, that's when you actually assign the material. Okay. Okay. And so that's all the new stuff. Question? Yeah. Yes. Yeah. So structural steel is always the default for this. Yeah. And so if you buy the commercial version of Ansys, they have a lot more materials kind of in their default library. But because this is the student version, they only have just the one structural steel. And so if you're making it out of anything else, you have to input it manually and then change it kind of in here as well.
So like, I would say there's no sense, but like, it seems kind of pointless to change the material in SolidWorks.
Yes, yes. Yeah, so changing the material in SolidWorks, that doesn't load in Ansys. And so you're gonna have to redo it again in Ansys. Yeah.
Does it load in any other?
So the file format that we use, the x_t, it really only saves the geometry itself. And so it doesn't load any of the extra metadata. Yeah.
I don't know who asked the SolidWorks one, but it's still good to be able to have that SolidWorks one because if you go on SolidWorks, then you can still see like that the Poisson's ratio on SolidWorks that inputted.
Yeah, that's a great point. And so, that saves you the trouble of kind of looking those things up manually. And so you can do it in SolidWorks and just kind of input that manually. Good questions. Yeah.
Is this a 3D versus 2D?
Yeah, so this is 3D. So everything from now on is going to be 3D. So the only activity that we did, which was 2D, was the first one.
I forget how to check that.
Yeah. So that's in Workbench. And so to check if it's 3D or 2D, you're going to right click on geometry and go to properties. And then it's something here. Yeah. And so it's line 21. But for the rest of the class, you're never gonna have to worry about it because it's always a yeah. So 3D is the default. As it should be, because we live in a three-dimensional world. Some people are out here playing 4D chess, but I live in the 3D world. All right, any other questions on this part here? Okay. All right, and so that's it for all the new, I would say the new knowledge. And so, activity one, I think is kind of the roughest one in terms of, we kind of have to learn everything from scratch. But what you'll see for all the future activities, we're going to build on that. Okay. And so, but before I let you go, I do want to expand this meshing section a bit more, because the only thing that we did, at least as a class together, was we only changed the size of the mesh from here. Okay. And so if we generate the mesh, right, we can change this size. So that's actually a pretty crappy mesh. And so, if we change this to, let me change my units, change it to millimeters. Okay. And so let me change this, let me make the mesh size 5 millimeters. Okay. Just to see. Okay. So that's a bit better, but we can do even better than that. Right, so this is basically all we did on the first activity, was I had you change the element size from here. Okay, but there's actually a lot more that we can do with the mesh, and it's especially going to be relevant, given what we're talking about in the lectures. Okay? And so the main ways you can kind of add more some fine control of your mesh is to add what I like to call meshing objects. Okay, and so the way you do that is you can right click on mesh, and then you go to insert. And then you can add all different kinds of these meshing options to it. Okay. And so first thing we're do, let's add a sizing object. And so the sizing object, what that's going to do is that it's going to allow you to assign a mesh size to your object. Okay. Okay. And so if you click on sizing, you can see that it created a new object here called sizing. Okay. The only thing is that if you're using these meshing objects, you have to assign a part of your geometry that you want to assign these settings for. Okay. And so you'll see here that there's two things that are highlighted in yellow in the details window. So there's the geometry part, and then there's the element size part. Okay. All right. So the first thing we need to do is we need to assign, the part of the geometry. Okay. And for this particular model, we're going to assign this sizing to the entire geometry. Okay. And so the way you do that is you have to click on this kind of little box right here. Okay. And so what that little box does right there is it tells Ansys that you want to select a volume. Okay. As opposed to a surface or a line or a point. Okay. And so you want to make sure your selecting mode is you're selecting the right parts of the geometry. Okay. So let's go ahead and select this entire part right here. Okay. So it should all kind of highlight green. And then you're going to go to geometry here and you're going to click on apply. Right, and then the last thing we're gonna do is we're gonna specify the size. And so what size we use? We use 2, so let's try 1.5 millimeters. Okay. Let's go ahead and generate the mesh. Right. So you can see here we have a much finer mesh. So this might be a little bit overkill, and so but you know, you can play with the size. And so you might be asking, you know, that basically did the exact same thing as changing the mesh size here, right? And so if we change it here and we change the sizing here, you know, what's the difference? So why do we have two things? Well, the big difference is that when you change the mesh size with the sizing object, you can actually choose different parts of your geometry to have different mesh sizings, right? And so, you know, let's say that, you know, instead of selecting the whole body, what we want instead is we want to select, you know, just this edge right here, okay, or just this surface. Okay. And so what that tells Ansys is that, you know, for the majority of the mesh, we're going to use this kind of default sizing right here, which is found from the mesh, actually the mesh overhead. But then the sizing object, what this will do is that it'll allow us to kind of refine just certain areas of the mesh, right? And so let's see what that looks like. And so actually, let me make this 3, just so you can see a bigger difference. Okay. Right, and so it's a little bit hard to see, but you can see, but you know, if you can see from here that most of this mesh here is meshed with, you know, fairly large elements. But then if you look inside this hole, right? If you look inside this hole, it has a smaller size because we specified this to be a smaller size here. Okay. And so you can use sizing objects like this, where, you know, if you want to have higher mesh density or smaller elements in certain areas of your geometry, you could do that with the sizing object. Okay. Okay, so let me actually change this back. So let me change this to 2. Okay. And so I'll leave it up to you to decide, you know, if you want to refine certain areas of the geometry, you know, and you can kind of play around with that. But for this activity, you can actually, you know, get away with just using one size for the whole thing. Okay. Okay, so that's body sizing. Question, yeah. Yeah, so refinement, that's a good question. And so, you know, if you were following the PDF from activity 1, you'll see that you'll see that there is an additional control here called refinement. And so refinement is just another way to refine the mesh in a certain area. And so it's kind of 2 different ways to skin a cat. It's just the way that they achieve the refinement is a little bit different. And so the way that this refinement works is that it takes kind of the global mesh size, and then it kind of cuts down the size by a factor of that global size. And so this is a little bit better if you want to refine around a hole specifically. And so what you can do is you can add a refinement around like an edge, and then it'll refine the mesh really cleanly around that edge, versus if you try to apply like a different size around that edge. And so this does it, I think, a little bit cleaner on kind of hole edges and things like that, versus the sizing one. And so, you know, in the end, they kind of do the same thing. It's just how they do it is a little bit different, and you get a little bit cleaner results using one way or the other way. Yeah. Okay. But for this activity, you don't need refinement, but that's kind of how it is. And so the other thing that we're going to do is we're going to add a method object. And so this one's actually a bit more important. Okay. Right. So we're going to do method. So we're going to right click mesh and then click on method. Okay. And so that's going to create another meshing object here called method. Okay. All right. And so just like the sizing object, we need to apply it to a certain part of the geometry. And so for this particular case, we're going to apply it to the entire geometry. So make sure you're on volume select mode and you click on that. Okay. So click on apply there. Okay. And then there's actually 2 settings here that are important to specify. So there's the method, which specifies the shape of the elements. And then there's the order of the elements as well. Okay. We haven't discussed order yet, but you know, for this particular simulation, and basically anytime you want to do a structural simulation, you should use quadratic elements. Okay. And so make sure you change this order here to quadratic. Okay. And then the method, this tells you basically which shape that you can use. Okay. So actually you guys have practiced this already. So you guys have already done triangles, right? But now that we have a 3D geometry here, we have different options because it's a 3D object, right? And so right now, you know, these triangular looking elements here, these are called tetrahedrons, but we can also use hexes, which are hexahedrons, which is their fancy name for a box, basically. And so, you know, if you want square looking elements, that's how you do it. Okay. All right, so let me go ahead and generate this mesh with a hex dominant element. You are free to choose, yes. I'm just kind of showing you the different options that you have. Okay. So generally speaking, tetrahedrons work totally fine, but you get kind of a little bit of a nicer looking mesh if you use hexes, right? And so you can see here that after I change the hexes, our mesh looks pretty nice, right? It's a very visually appealing mesh because everything is nice and straight and straight lines. All right. And so those are the primary two meshing controls that you're going to have. So, you need to control the size, but then you can also control the shape and the order as well. Right? And so, for this one, I'll let you choose. I think in the end, it's not going to make that big a difference which one you choose, but you can test it out and see which, how big a mesh you can get, how small the elements you can get, and what the different shapes actually. Okay. All right, any questions on this? Okay. All right, and so from here, it's, I'll let you guys get to it. And so, from here, the next step is the boundary conditions, okay? And I'm not explicitly telling you what boundary conditions you should apply here are going to be, okay? So you're going to need to decide that on your own, based on, how you think this bike crank is going to be loaded, okay? And so you can read more about that in the PDF here, okay? But basically, we're at problem 2 right now, okay? So loads and constraints. And so I will give you a couple hints. And so at the very least, I want you to add a fixed support somewhere. Okay. And so anytime you run a structural simulation, you need to fix it. Okay. And then additionally, I want you to add a force load as well. Okay. And so at the very least, you should have one fixed support and one force. Okay. And so think about how this bike crank is actually going to be used in practice, right? And so if you need reminders, you can unsuppress the pedal. Okay. Right, so remember the pedal is acting over here, okay? And so if you think about how a bike crank is used in practice, the person is pushing down on that pedal, okay? And so if the pedal is on this side, that means that the bike crank is going to be attached to the bike on the other side. So these 3 holes here for attaching to the bike, right? And so you have to think about, what makes the most sense in terms of, where you apply the load, where you should fix it, and what direction the load should be, okay? And so the only constriction on the load is that it should have a magnitude of 100 pounds. Okay? But where you apply that, what direction you apply that, I'll leave that up to you guys. Okay? All right, so you guys can go ahead and get to it. If you have any questions about anything, you can raise your hand and I'll make the rounds, and then yeah, just go ahead and work on this. And so ideally, at the end of today, you should finish up to problem 6. And so if you can finish up to problem 6, the first problem 6, and so there's 2 problem 6s, unfortunately, it's a typo, but if you finish up to the first problem 6 today, then you'll finish everything that has to do with this Cad file, and then you don't have to take it home. So if you can do all that today, get your screenshots, get the answers to the questions, then you're going to be in great shape for this activity. Yeah. Oh, question. Okay. I'll come around. Yeah. Yep. Yeah. And so when you put generate mesh, it kind of destroys your previous mesh. But if you're just making them small, it's going to update the new part. So this math. But I always do generate just because I've worked with software. I have the muscle memory. I think they updated. Yeah, but the updates are just making some. It's the same. It's the same. So updater for the entire. Oh, you can change the units. I went to change it to millimeter just.
But yeah, so a lot of people have that issue. It's a resolution. So you need to kind of change. Mismatch with what's. Yeah. Yeah.
Oh, are you doing body type?
Well, body size. Okay. Yeah. I think the one it doesn't have to look like that. Although I realize now that that's the fourth thing I do. Sorry guys, you have a question? I know. Okay. Your mesh was pretty wide, so might be having so the body sizing one will actually override this. It looks like 1.5 is really small, especially for us. So try changing that to 2. 2 is probably the smallest. That's pretty cool. It's interesting actually. So you think that changing it to 1.5 is like, but it's actually because we're and so it changes actually different. Actually too big. That's fine. And so so the text is dominant. Yeah. And so it's really hard to make a mesh that completely all text. So it might be part of the geometry.
Yeah.
But that's totally that's no good. So in the grain geometry,
Or not only bending out the quadratic.
it might be close.
Just because like if you do
And this is very
Oh, Eric. I was gonna do one of them. Expression,
Right. Remember the
I can. Yeah, I.
there's some and we'll run this next. We have this.
Is the only one. The pedals coming out of it.
Oh, what if they're so negative?
So if they make contact, then they will, I guess. I think both will work. Just that this way will like but they're both valid.
I've got one more question. How much?
So how?
It sounds a lot.
Okay. I think for the activities, it's actually not that many.
Yeah, towards the end of the play.
Yeah.
Experience the most force when a person's doing it. Yeah, then you should be able to save it to others.
Well, that's one way to do it. Yeah, that's one way.
So,
Yeah, well, but for this particular activity, you're saying one. But generally, if you have a longer object like this, the worst case.
oh, yeah.
That's gonna cause a lot more stress.
Yeah.
So if you.
So that pressure.
Right now, it's probably not
I think it might be there.
force. No, the
Force. So he says.
What I find
Because this part is stronger than this part. Also, you're basically, down.
So now you can apply it. Ah, okay, so for a hex, so someone does. So hex is it's impossible to get, it's usually impossible to get like a very mesh.
Maybe it's just this entire. Instead of like, maybe it's
Unless your geometry is perfect. So what's gonna happen is that some. So generally, random directions. One point five. Oh, wait. Check Zoom.
All right, Zoom people, do you guys have any questions? Okay.
Yes, how do you change?
Yeah, go ahead. Ryan, go ahead. I think you were the first one.
Does that make sense?
Yeah, so I think people have been getting that warning too. So all that's basically saying is that there are, when you have a geometry like this, it's impossible to get the entire geometry with hexahedral elements. And so it has to put some prisms and some triangles somewhere, and that's totally normal. And so if you can cut down on that percentage if you lower the size. And so for this one, I have a size of 2. But if you make that size higher, it's going to give you a higher percentage. But that's fine. So that's a normal thing. So I wouldn't worry about that. Yeah. No. It's not detrimental at all. It's a normal thing. Usually before it never gave that warning, but I think it's a newer feature in the newer version.
I got the same thing.
Yeah, okay. Because in this one I'm running 2021 and I don't get that message at all. But I think for those of you running 2022, I think that might be a new thing that they're doing. Yeah. Yes, yeah, and so when you're applying the load, the most convenient is to switch it to US customary so you can apply it from the bounds. Yeah, I mean, so tetrahedrons are triangles, and so tetrahedrons are just 3D triangles. All right, Jaden, you had a question too? Okay, awesome. All right, I'm gonna go back. So some people have questions here too. Yeah.
Yeah. And that's when the pedals down. It's not actually like the rotation part. Yeah. So we're applying just the X direction.
So that's the right application area. And so I'll let you, you can run, the beauty of finite elements is that you can run the simulation in multiple different configurations. And so, I would definitely try this out. That's definitely a good something to try. But for a long object like this, you have 100-pound force. Think about, what's the worst direction that you can put in possible stress. So generally, for an object like this, put in bending, that's usually the worst. That's kind of
perpendicular.
Exactly. So it's hard.
It would be in the y direction.
So you can try it. So I would definitely encourage you to try it in tension and then try it in bending too. And then look and see what the difference in the stress is. So that should tell you, which is kind of. But yeah, just try both. I mean, that's the beauty of finite elements. Try both.
Should I do both at the same time?
Do one, look at the results, and then change it. And then or one of you can try one, the other see.
Oh yeah, this is oh yeah, because yeah, this is applied a little bit more. This makes more sense because this is applied.
Okay. I'm gonna set this to a y. Do I just?
Oh.
This would be negative y, sure.
That's what we did last time. I'll check the okay, so we don't. Next one comes to we're just going to close the information. Equivalent stress is what this is. We don't need those.
Well, think about
We can change time back to the next direction. I'm pretty sure. Should have changed it.
So this part right here. Oh, yeah. You know, this whole thing is actually something. I'm actually not that big of a fight.
Yeah.
Someone asked me about something earlier, like something about, I know this. Yes. I just talked about it. Another question? Yeah. Right. Yeah. I would say you can only do this. It's either gonna be 100 pounds of X.
Your max deformation.
And positive negative. Any questions? To go help your. Yep, that's all I did for mine. I actually suppressed the title and I suppressed that part. The fixed support, that's basically just where, you know, the part of the object that's not supposed to be. Usually you add your fixed supports wherever this part actually attaches to something else. That's where you add it. In this case, no, it's right here. There's where the title attaches to like that's where it's.
So the basically the actual.
Yes, exactly.
And those two holes are
Within those systems. This particular case, these holes right there, that's going to
From stopping. Yours is great.
That's why I define it to get it as well.
Because the structure.
So we're going to assume that's so you're right.
Yeah, you're applying.
So like, but for this,
Flying.
the way I did it like that.
So when I imagine you wouldn't be with this structure, you would do more damage.
Well, good.
This is fixed.
Oh, I hear you.
We all need on each
So on the actual.
Hands on machines and stuff.
Right. Let's go back.
All of these guys are here.
Right now, we will slide on that line.
These holes.
Frank is slide on. And so unfortunately, you know,
Now.
Why did you take the?
I can't see. I'm pretty sure they're just. This whole. The whole part of example.
Realistically, we'll never have I figured it.
You said you should not take it.
Check Zoom real quick.
Yeah, there's a lot of people talking.
Yeah. All right, sorry, Zoom people, I'm back. Any questions? All right, so it looks like, yeah, so you want to apply the force, yeah, using component. I usually use components most of the time because that I feel like that gives me more a greater degree of control. Because the vector one assumes that it's always going to be pushing into the surface. Yeah. Did you guys have any other questions? Okay. That's fine. We need the but last year, some just, I don't know if it's a computer thing. But some people just, the X just wouldn't work out. I don't really know what that is. So, and so if it's not working, no. Yeah, so we'll learn this maybe. Yeah, or this one is so reduced, it's so energetic, why it doesn't work for certain geometry. Yeah, so the text distribution is helpful, so tetrahedron. It's just that a little bit nicer to use. Yeah, catch that. Yeah, so sometimes people come like.
That's what I should.
I knew it was somewhere. It was not just. Okay. Okay, so right now, all your results. Right now, you see full if you want to think that's like, unfortunately, I don't know how to do it. So just have to just make sure that when you bring that. Yeah.
So it's based on the entire.
Because of the orientation part. Yeah. Mark's already oriented towards X and think about it.
Yeah, so
It's orientation for the right force. Our next points downwards, or what would be downwards instead of Y. It's already oriented towards the X and if we were to simulate it going down, the force going down, I had the force to this right here going towards the X direction. That's if we rewrite it by, at least it's in the Y because the Y part is going just because that's the way the part was made. The part was made vertical. Down.
okay. So
It's just the way the part was made.
Yeah, I guess.
Instead, we're going to define failure. And so right now you're not here. And so the maximum is somewhere between. Try to find the amount.
That's this first one. I suppose the first
Chat. Okay. All right, so we have about 8 minutes left, and so I just want to, go over, I know some people are kind of in different places here, but I want to make sure that we all kind of are on the same page with kind of what you're supposed to do. Okay. And so most people are at this point where, you apply the force. And so what I've been telling people is that, this 100-pound force, you have to choose the direction. And so, I know some people have gotten creative in applying it in a diagonal direction, but I think the best way is to actually just, apply it is either X, Y, or the Z. So just kind of keep it simple. And so, I think that's the best way to do that. Okay. Okay, so problem 3 is predictions. And so, you can see, just make a prediction on how you think the simulation is going to go. Okay. But the one that is important here is actually problem 5. Okay. So problem 5, I want you to use the finite element simulation to predict at what point this bike crank is going to fail. Okay. So what I tell you is that aluminum 6061 has a yield strength of 35,000 psi. Okay. And so if you remember, from our strength of materials review, that means if the equivalent stress in the bike crank exceeds 35,000, that means the bike crank is going to fail. Okay. And so what you're going to do is you're going to run your simulation and first check and see if the stress is under 35,000 psi. Okay. And so the units here are important. So when you're in mechanical, make sure that you are in US customary with the inches, just so that you can see psi. Okay. But it's not just 35,000 that I'm asking you to look for. So I'm asking you to look with a safety factor of 2. Okay. And so if you remember, from one of the earlier lectures, that means that the actual yield strength that you're actually going to be looking for is not 35,000, but it's going to be 35,000 divided by 2, okay, which is 17,500. Okay. And so what you're going to do is that you're going to run the simulation, make sure that your equivalent stress is less than 17,500, which should be under 100-pound load. And then what you can do from there is you can increase the load. And so instead of 100, maybe you do 110 or 120 or 130, right? And so you should keep increasing it until you reach the point where your stress is 17,500. Okay. And so this is kind of the power of finite elements, where you can try multiple configurations, and it's very quick to kind of do so. Okay. And so you're probably going to have to run, 3, 4, 5 simulations on this part in order to get the correct load amount. Okay. And so that's kind of what you have to do in part 2 right here. Okay. And then in problem 6, the last one, for this part anyway, is I want you to change the direction of the loading. And so instead of loading the bike crank, well, okay, I'll tell you right now. So the configuration that's going to lead to most stress is if you load the bike crank in bending. So if you put the 100 pounds in the Y direction, that's going to lead to the most force. Okay. And so in problem 6, I want you to compare that to if you loaded it in compression. And so if you took the force and put it in the negative X direction instead, okay? And so you put the force in the negative X direction, and then you're going to repeat that process. And so, you're going to keep increasing the load until you reach a stress of 17,500 psi. Yeah, and so to do that, you need to change the units to the other US customary, so the second one. Yeah. So 17,500 psi, that's kind of your magic number for the stress. Okay. All right, so we have 5 more minutes. So there is a class after this, and so if they kick you out, they have to kick you out. But I think some people could probably work in the back if you're quiet. So if you want to stick around and kind of keep working on this, you can. But we do have 5 more minutes left in the class, so I'll keep coming around for 5 more minutes. Yeah, so saving it. So if I've seen a lot, excuse me. So I've seen a lot of people today work on their own laptops, which is brilliant. So you don't have to worry about file transferring. And so to save it, if you're working on your own laptop, the best way to save it is just to use the save command right here. And so, if you're going to be working on the same computer here and at home, then using the save command will just save it on your local computer. And then what you can do then is you can just open up the file from your computer. Okay. But if you're moving the file, and so if you're working here on the lab computers and then moving it to your computers at home, then what you need to do is you need to click on archive. But unfortunately, I don't think that's working out super well because the version is different from the laptop to the computer. So, if you, If you're working on the lab computers here, I would recommend just get as much done as you can from the PDF. Get the screenshots. And so, if you read the PDF, you'll see I'm asking for certain screenshots. Get the screenshots that I'm asking for, put those in a document, and then take those home. So you don't have to repeat that. At home. Okay. All right. And so I'll come around for the last 3 minutes. And then, after that, we might have to skedaddle because the next professor's going to be. Especially so I agree with you. Oh, yeah, yeah. When I tell you it's a computer, try it. See.
I have no idea. I guess we
Whenever you mesh, do you like meshing like in general and the body sizing to be equal to each other?
So you don't have to. So we did that in this case because we just applied the same size. To everything. I was just kind of showing you that you can do it either way. So where the body size comes in handy is that there's only certain parts of your model that you want to mesh with a certain size. So then you can kind of modify different.
I just make them equal and then it visually looks better, I found, but mine is like 7.3.
Okay.
Triangle, I can't do hexagon.
Some people can't, and like I was talking to some guy over there. I don't know what it is. I haven't figured it out for like, it's been 4 years now. It's just some computers just can't do a hex mesh on this activity. I just don't understand why that is.
Well, this is a my laptop too.
Yeah, it's not because like some of these computers are brand new in the lab, and like he wasn't able to do a hex mesh on his. So I don't know what it is honestly.
It says it can, but it just says it's way. It's like there was a finite mesh problem of 16%. I was always getting that.
I see.
And I try to get lower and lower and lower, and then it says cannot do it. I'm like, okay, I give up. I'll do a triangle.
Yeah, just I mean the triangles are going to be reliable. That's always you're always going to be able to do. Jaden, do you have any final questions?
I do. So when we go to problem 5 for the maximum load,
yeah,
and then we have the yield strength of 35,000 psi, safety factor of 2.0. We're basically just increasing our force number until our maximum on the normal stress, or sorry, on the equivalent stress reaches 17,500.
Exactly, right. Yep.
Okay, well, perfect. That's it.
Awesome. Cool. I'll see you next week.
Cool. Thank you.
I'll jump